Log on, tune in, find out. Another good idea from Cambridge.
Yuval Rabani, as you can see, well, almost, you can guess. And he's talking about Rademacher chaos, random Eulerian graphs, and the sparse Johnson-Lindenstrauss.
Okay, this is probably going to be a rather short talk, and reading the title takes most of the time here. It's already been done. So the topic of this talk is dimension reduction, and the main tool here is this famous lemma of Johnson-Lindenstrauss that says that certain random projections of Hilbert space onto a low-dimensional subspace preserve approximately the L2 norm of a vector. So if we project onto d dimensions, and I'll explain in a little more detail about the distribution that work. If we project onto d dimensions, then any vector in the space, its norm is preserved up to a factor of 1 plus minus epsilon, with probability at least 1 minus something that's exponentially small in epsilon squared times the dimension. So in particular, if you want to reduce the failure probability down to some parameter delta, what you would need is order of log 1 over delta times 1 over epsilon squared dimensions.
So L2 is Hilbert space, right?
Yes.
Infinite dimension.
Yes, but in fact, finite dimension is what we need because we're looking at finite point sets. I'll restrict my attention to finite dimensional spaces. So, for example, if we have n points in Hilbert space, then, and you want to preserve all the interpoint distances, so that would be n choose 2 vectors, then what you need is dimension 1 over epsilon squared times log n times some constant. Just in terms of terminology that I'm not sure I will even use, so if there's some finite subset of Hilbert space, a linear mapping that approximately preserves the norms of these vectors is nowadays called a JL transform. This lemma now or recently found many applications. I'm not going to quote many references here. I'll just talk a little bit about them. So originally, there are applications in pure math, originally in functional analysis, in particular for extensions of Lipschitz maps, in graph theory, and since Linia, London, and Rabinovich introduced this lemma to computer science, and later on Kleinberg used it to design an approximate nearest neighbor search scheme, it's been a very popular tool in various problems that have to do with data analysis and processing massive data sets and high-dimensional computational geometry. So here's a partial list of these things. It's been used in approximate nearest neighbor search in high-dimensional spaces. So this is a problem of processing a database in order to answer proximity queries. You get a point as a query, and you want to retrieve a near point in the database. This turns out to be hard when the dimension is large, meaning that it can't be treated as a constant. So it's relatively easy to do if you are willing to spend time or space that's exponentially large in the dimension. But when the dimension is high, you don't expect to be able to do that. And then people need to resort to finding approximate nearest neighbors. And the Johnson-Lindenstrauss lemma is useful there. It's been used in learning mixtures of Gaussians. I'm not sure the most recent results use it, but it's been used in the past to do that. It's been used to design streaming algorithms. There, the issue is processing data that arrives piecemeal without storing the entire data. It's been used in communication complexity, the problem of computing something over an input that's partitioned into two parts, and you want to transfer only a small amount of information between the two sides. And it's been used in signal processing. So in all these applications, the main feature is that dimension reduction allows you to compress the data in a way that doesn't distort distance information too much. And in some of these applications, it's important that the dimension reduction transform is linear. Specifically, I think in streaming, possibly other applications. Also recently, it's been used as a tool to speed up linear algebraic computations. Essentially, if you want to decompose matrices in various ways, it's nice to reduce their rank while approximately maintaining various properties. So that's where it comes up there. What we'll be interested here is in some computational aspects of the Johnson-Lindenstrauss transform. So I'll talk generally about various computational aspects, and then we'll focus on one specific issue there. So the issue is important because the lemma has applications to massive data sets, and you want to be able to compute the projection quickly. The first issue is how complicated is it to generate a random matrix with the desired properties, and it turns out that very simple sample spaces suffice. So the original proof used a linear subspace that's random, that's uniformly chosen from the appropriate distribution. It turns out that you can use independently generated uniform random vectors from the unit sphere. And you can use even simpler distributions. For example, you could take matrices that have independent and identically distributed entries from the set -1, 0, and +1. And that makes computations much easier than dealing with real numbers. And in fact, this is a special case of a more general claim that if you take independent sub-Gaussian entries with the appropriate variance, that that also works, or that always works for any such distribution. What about doing things deterministically? So you're given a set of points. This is sort of a standard setting. You're given a set of points and you want to project them and preserve all the distances, all the Euclidean distances approximately. Then I'm not sure if all the probabilistic constructions, probably all of them, but definitely most of them can be de-randomized using the method of conditional expectations. And this can be done directly or through pseudo-random generators for log space. And that gives a deterministic construction. Let me continue with that and then I'll go back to these two other points. The drawback is that this is an adaptive de-randomization, so you need to know the set of points in order to do it because you need to check things as you go along, as you're generating the matrix deterministically. And until recently, this required a truly random seed of at least log square n bits for n here is the number of points. So we're talking about the setting where you want to project n points and preserve approximately the distances. There are very recent results that reduce the randomness down to log n, log n. Now this still means that the number of possible projections is super polynomial. Now existentially we know that there is a polynomial sized set of projection matrices such that for any set of points, one of them is going to work, but we don't know how to construct such sets. And this is the best that's known right now. So let me just go back here. There's some recent work, some of it mentioned in the next slide about explicit construction. I won't go into that. There are explicit constructions of the form that I'm talking about, polynomial set of matrices, but the failure probability there is bigger than what the Johnson-Lindenstrauss lemma guarantees. So there's some other work concerning de-randomization, but the problem isn't completely solved yet. Also, another comment is that the dependence on epsilon in the dimension is optimal, and that was shown to be near optimal by Alon, and very recently J-Ram and Woodruff showed that indeed it's optimal. You can't go below 1 over epsilon squared. Okay. Now there's something called the fast Johnson-Lindenstrauss transform. This is summarized in the following theorem. So now we're talking about how quickly can we compute the projection of vectors. How quickly can we apply the transform to vectors? There exists a random projection matrix. The matrix is produced randomly. But once you produce it, you can transform vectors much faster than you would for sort of the vanilla version of the JL transform. If you have a transformation from dimension n to dimension d, in general it would take you n times d arithmetic operations to project one vector. And here it can be done in time order n times log d. So these are results by Eilon and Chazelle, and improvements by Eilon and Liberty, more recent improvements. And roughly this is how it's done. So I'm describing here the later result that improved the first breakthrough result. So here is roughly how it's done. There are two stages, and these two stages are sort of what happens in all the fast implementations of the JL transform. There's a preconditioning stage where you don't reduce the dimension necessarily, but you convert the vectors into a nicer form. So you rotate them in space in a way that they will be somewhat smeared. Usually what you want is that some norm higher than 2 of the vector, of a unit vector, will be small. So here the preconditioning is done by applying a constant number of Hadamard transformations with random signs. So you take the Hadamard matrix H, you multiply it by a diagonal matrix that has uniformly at random plus minus 1s on the diagonal and 0s elsewhere, and you do this a constant number of times, and that generates, that transforms any input vector into something nicer. And then comes the projection phase, and the projection phase here is actually deterministic. I think that wasn't the case with the first result, it's the case with the second result. So you take a matrix whose columns are points in a 4-wise independent sample space. So what I mean is that you can think of the rows as your variables, and the columns are possible assignments of values to these variables, and you want if you want the rows to be 4-wise independent if you pick a random column. So one specific way to do this is to use dual BCH codes. And then the final transformation is to take this matrix B, this deterministic matrix, to multiply it by another diagonal plus minus 1 random matrix, and then multiplied by the preconditioner, and this chain of multiplications gives the transform. So maybe I have plenty of time. So maybe one word about how they proved that this works. Well, the computation is fast. So I won't talk about why it's easy to compute this. It's mostly because it's easy to multiply Hadamard matrices. To multiply a vector by an Hadamard matrix. That's the main reason it's fast. Why does it work? The proof looks something like this. Instead of writing the transformation this way, you can write it as B times a diagonal matrix where this vector phi times x is on the diagonal, and then times plus minus 1 random vector. Now, phi takes care, phi and the structure of B both take care that B times this diagonal matrix is going to have a small operator norm. some specific operator norm. I won't go into the details. And then what you're looking at is you apply this operator on the binary cube, on the plus minus 1 to the n. That's the vector you're multiplying. And this is highly concentrated around the mean, this operator, because it has a small norm and it's convex. So it uses Talagrand's inequality for such things.
To multiply b by the vector is quick
because they use a specific b. They use a dual BCH. Yes. The proof that it's a JL transform doesn't need specifically the dual BCH thing, but in order to prove the computation time, they need it. Okay, now we're getting to what I want to talk about, and that's the sparse Johnson-Lindenstrauss transform. So the motivation here is the following. Suppose you want to apply the JL transform to sparse vectors. So you want to project sparse vectors. Then if you manage to do that using a sparse matrix, and the parameters are right, then you might actually be able to compute things faster than the fast Johnson-Lindenstrauss transform. And this is something that I'm told comes up in applications. Not sure about the details, though. Dasgupta, Kumar, and Sarlos introduced the question, and they also gave the following answer. They showed that there is a random matrix, a random transformation matrix, such that which is a JL transform. And in each column it has order of 1 over epsilon, log square 1 over delta time, log square n over delta, log 1 over delta, non-zero entries. So of course this only makes sense when epsilon is thought of to be very small, something which is not a constant, even smaller than a constant. And that often comes up in applications. Sometimes you want a JL transform that is very accurate and you're willing to pay in the dimension, but you don't want, of course, to pay too much in the dimension. So for sufficiently small epsilon, this would beat what you would get from a vanilla version JL transform, which is potentially all the column is non-zero. Is non-zero.
Is it clear that this has to tend to infinity over there? That this cannot be done with something that's...
Yes, there is, I think, a square root of log n lower bound. If I'm not mistaken, there is some lower bound that shows that. But actually, n here is not important. It's the delta. But you can think of delta as being 1 over polynomial in n. So I think it has to tend to infinity with 1 over delta. But it could be square root of 1 over delta, as far as I remember. And that's also in this paper. Now this bound was improved a few months later by Kane and Nelson. So they gave they shaved off one of the log square n over delta, one over the log n over delta terms. And I want to explain the transform here because this is what we're going to analyze as well. So this improvement is using the same transform, and our results, which I'll eventually get to, also use the same transform. So again, there are two stages here. There is a preconditioning stage, and then there is a projection stage. The preconditioning here is essentially trivial. You take the vector and you duplicate coordinates. So the preconditioning actually increases the dimension. And you duplicate each coordinate c times, and then of course you need to scale so that unit vectors remain unit vectors. So C here is going to be the bound on the sparsity. So the entire sparsity comes from the preconditioning stage. And of course, this preconditioning, as the next slide will summarize, reduces the L infinity norm of the vector to 1 over square root of C. So that's the property that is required from the preconditioning. Now, what about the projection? So we want to project a vector from dimension C times n to dimension D. And we'll use a projection matrix H. And the projection matrix H is formed as follows. In each column J, you pick one position, one row uniformly at random. We'll denote that by H of J. And then in that particular place, you place either +1 or -1 with probability half for each option. And the rest of the matrix is zeros. So this matrix H is extremely sparse. It has only one non-zero entry per column, and the sparsity bound comes from this preconditioning phase. So this is the entire construction. Now, you don't really need complete randomness here the way I'm stating it. You can also reduce randomness, and in fact, all these two papers and the one that I'm eventually going to talk a bit about all show how to reduce randomness, but I don't want to go into it here. So this is a somewhat simpler way to view it. So the entire transformation is taking this matrix H and multiplying it by the preconditioner P. Okay, so what did we do with this? We improved a little bit on the sparsity of this construction, on the proof of sparsity, and we showed that instead of taking 1 over epsilon times log n over delta log 1 over delta, you can take 1 over epsilon times log square 1 over delta divided by log square 1 over delta log square 1 over delta. So the improvement is this log divided by log squared. What?
You are independent of n. Before there was some n.
There was some n there, but the n there is, yes, we were independent of n. But really, delta is sort of much smaller than, delta to the -1 is bigger than n, so it really doesn't matter much for all practical purposes. Now, of course, this also is useful when epsilon is very small.
You can consider situations in which you don't care to maintain all these things.
Yeah.
That does not have to be.
Yeah, that's right. So if delta is relatively large, then this is maybe a significant improvement. But sort of normally, I don't tend to think of delta as large. Okay, so I want to show you a little bit about what we did and why this may be interesting in some sense. So let's take a unit vector x, and I want to denote by y the vector after the preconditioning. So we'll work on a vector y. Y is in dimension c times n, and what we know is that the L2 norm of y is also 1, and the L infinity norm of y is 1 over root c. So that's what the preconditioner takes care of. Now if we write the, so this is the entire transformation, h px, And we want to look at the L2 norm squared of that projected vector. That's, of course, the L2 norm squared of hy. And this is just the sum over all pairs ij of some coefficient hij that I'll soon discuss times yi times yj. And you can really easily see that the diagonal terms here sum up to 1. So this is what we hope to get, something close to 1. And then the error term is the sum over all the off-diagonal terms of hij, yi, yj, and we'll denote the sum by z. Now, what's hij? Hij is given here. Hij is this zeta I times zeta j. These are both plus minus 1 random variables independent, zeta I times zeta j, times the indicator of whether or not the row chosen for column I is equal to the row chosen for column j. So if these two columns choose different rows, we get a contribution of 0, and otherwise we get a contribution of 1 here. And this is hij. So in order to motivate the title, z of such form, sum over I not equal j, xci times some coefficient, which will be this indicator times yi, yj, that's called an order 2 Rademacher chaos. And we use the conventional method. We want to bound the deviation from 1, the probability that we deviate from 1. That's exactly the probability that the absolute value of z is bigger than epsilon. And we take some high even moment of the distribution. So instead of that, we look at the probability that z to the 2m is bigger than epsilon to the 2m, and then we use Markov's inequality, and that's bounded by the expectation of z to the 2m divided by epsilon to the 2m. So everything boils down to showing, to bounding some large even moment of z. I'll just mention that the first paper bounded the moment generating function, and the second paper followed this approach of picking a specific moment and bounding it. So what we're going to show is that this high moment of z is small. We're going to show that it's bounded by some small constant times epsilon to the 2m, and then if we pick m to be sufficiently large, then we get the bound that we want. We get that this probability is smaller than delta. Okay, so how do we bound this moment of z? We're going to show a correspondence between what happens with z and counting certain types of graphs. So let's look at the set of all multigraphs G that have nodes 1 through c times n. So the nodes are going to be the dimensions, the coordinates of the source of the vector y. And these are going to be multigraphs, so the same edge might appear several times, but they don't have self-loops. And they have exactly 2m edges, which we will denote generically by E1 through E2m. So EI, again for notation, I think I'm going to use it just in this slide. EI is, EJ is SJ1, SJ2. These are the two endpoints. These are the two coordinates that are the endpoints of the edge EJ, and we're ordering them so that SJ1 is smaller than SJ2. Now we can write a term Z sub G. This is going to be the product over all of these edges of the zetas of the endpoints, the coordinates of the endpoints, and the indicator that these two endpoints chose the same row. So this thing is just, if you take Z, take it to the power of 2m, and now expand it into a sum of monomials, this is just going to be one of those monomials. So, so in fact, we can write this expectation of Z to the 2m as 2 to the 2m, and 2 to the 2m comes from the fact that here we're using ordered pairs, and Z has each pair appearing twice, times the sum of expectations of these ZG. So really what we want to do is to compute to bound the expectations of these Z sub Gs. Now this is a very simple observation that the expectation of Z sub G is often 0. Why is it often 0? Because what you get here is you get here these zetas to some power, and whenever the power is odd, zeta is either +1 or -1 with probability half for each possibility. So whenever there appears a zeta that's odd, with an odd degree, then the expectation is going to be 0. So in fact, the only G's for which the expectation of zeta G is bigger than 0 are G's where all the degrees in this graph are even. And that simply means that such a G is the union of disjoint Eulerian graphs. So now we want to bound these things, and the sort of intuition here, the intuition that we'll use is that there are of course a lot of terms here. I mean, there are different G's and they behave differently, but essentially you can think of the following. So there are, I'm ignoring isolated nodes that don't appear at all, that appear with degree 0. If we focus on the nodes that actually appear, that have an edge adjacent to them, then if G has a small number of nodes, then the graph is dense, and that's not going to be good in terms of counting how many such graphs are. But on the other hand, that's a rare event. So there are very few G's, or there are relatively few G's that have a small number of such nodes. On the other hand, if the number of nodes that have an edge adjacent to them is large, then the graph is sparse, and then we'll have fewer possibilities for such a graph. So this is essentially the intuition behind the proof, and I'm not going to show you the entire proof. A lot of it is technical and uninteresting, so I'll show you what I think is more interesting here. The main observation here is the following: that we can actually reduce the estimation of this sum to a question about counting certain types of graphs. So let's look at a particular graph that we want to look at, G. It's composed of some connected components, which are denoted here by G1 through GT. So T is the number of connected components, and I'm ignoring isolated vertices that don't appear in the term. Then this expectation is just the product over all the connected components, where in each connected component, so this, right, has a probability of 1 over d of occurring. I mean, the indicator is 1 with probability 1 over d, and the probability that the entire component is indeed connected is 1 over d to the power of the number of nodes minus 1. And then you have to multiply it by a term which is each yj for each j in the connected component is raised to the power of the degree of j in the graph, which is some even number, at least 2. Now let's denote by u k to mt the number of multigraphs that have k nodes, 2m edges, even degrees, all of them at least 2, and t connected components. It's easy to see that in order for this to be bigger than 0, k has to be between 2 and 2m, and t has to be between 1 and k over 2. So if we look at this product up there, it looks something like this. So we're going to use the fact that the yj's are bounded by 1 over square root of c, and that means that we can bound this expectation by 1 over d to the k minus t. So the k minus t comes up from taking the product of that thing over all the connected components. You lose minus 1 for each connected components, and that's why you get k minus t. The 1 over c to the 2m minus k comes from taking upper bounds on the yj's, and then you're left with the product of yj squared. Now, if you sum this product of yj squared over all subsets of coordinates of exactly k coordinates, so we're looking at graphs that have size exactly k, then this is bounded by the 1 over k factorial is because you can take all permutations of the k nodes to the sum over all the coordinates squared to the k. Now this is a unit vector, so this is just 1, so the whole thing is bounded by 1 over k factorial, and that gives us the following bound on the expectation of z to the 2m. So I'm just plugging in all these terms, and you see that everything now is, these are just specific terms, except for this part. So really what we need to do, we need to estimate the number of Eulerian multigraphs on k nodes, 2m edges, and t connected components. And if we plug that in, we get a bound on the 2mth moment of z, which is what we need. So this is as far as I'm going to get. This is the main technical lemma in the paper. We show that there is some constant alpha, such that this number, the number of such Eulerian graphs, is bounded by alpha to the 2m times k factorial times m to the 4m plus k minus 5t times log 1 over delta divided by log 1 over delta, all this to the 4m minus 2k. Delta comes in because of the C, right? C contains something that depends on delta from here.
I just think you answered it.
No, still.
What?
We did answer the question.
No, still. I mean, the expression on the left-hand side is purely combinatorial. There's no delta, no nothing.
It's K, M, and T.
Oh, wait a minute. No, but M depends on delta. Sorry, right? We defined. Where did I define this? Here, we defined M to be. So yeah, you're right. This in fact, what is written here, you're absolutely right. It's log M divided by log M. That's what it is. I'm sorry. So I'm not going to go into the details of the proof. Again, it's sort of technical and messy and not extremely interesting. I'm just going to mention one aspect of it. The proof is essentially a case analysis. And there are three major cases. When the number of connected components is small, you get one behavior. When the number is large, you get a different behavior. And the difficult part is really when it's somewhere in between. And the reason why the first and last cases are easier is the following. In the first case, because there aren't that many connected components, you need to connect the graph a lot, and that very easily restricts the number of your possibilities. And in the latter case, most of the weight of the number of possibilities comes from choosing connected components of size 2. So connected components of size 2 are very easy because you have two nodes. So what can you do? You need to choose an even number of edges to connect these two nodes. And in fact, the log square delta minus 1 bound that was before, this is sort of the limit that you can get if you assume that if you look only at such components and assume that they overwhelm everything, all the rest of the behavior. So squeezing out this thing requires to look at larger connected components. So this case turns out to be easy because the connected components of size 2 is easy. This is easy for a different reason, and most of the work needs to be spent on this middle ground, where you need to take into account both types of components and somehow combine everything together. So good. So this is a good place to stop. Yes.
What about tightness of this
I
inequality?
don't know that it's tight, and you might expect that it's not. So it's not easy to count Eulerian graphs because it's sort of a non-monotone property. It's not a pleasant thing to count.
But it will not give the sharp bound. So
No, we don't even know what the sharp bound is.
Or the best thing you could hope for is epsilon
Yeah.
minus 1 log 1 over delta, right?
Um,
Like additional lower order terms.
Actually, it might even, I would conjecture that perhaps the true bound is epsilon, is square root of d. So it's epsilon, 1 over epsilon times square root of 1 over delta.
And you know that the counting cannot give that?
I don't think the counting can give that, no.
If you deal with the Eulerian graphs by the fact that there are unions of cycles, doesn't that help? There are sums of cycles.
Yeah.
Why does the-
Not that I'm aware of how to use it. Okay.
Other questions there, you should ask. You
Oh,
can only see.
yeah. Are there questions?
No, unmute.
Oh,
Mute it.
Alright.
Oh. Oh, good.
No, you're supposed to ask.
Ask either.
Are there any questions?
I think we are.
Okay, it's as disastrous as yesterday, right?
It's good.
The sound is disastrous.
Oh, okay.
Okay. Can I ask just one personal question? Do
Yes.
you plan to show up in Paris in the near future?
Who is this person?
I won't be in Paris next week if that's the question. I don't normally plan beyond 1 week, so.
Oh, you are hard man.
But I'll be happy to drop by at some point.
Okay. Thank you.
Any more questions?
Enough for us.
Okay. Any other questions? Who's the session chair? Right? Someone's supposed to do this thing.
At the moment. Alright, are there more questions? If not, then we'll thank the speaker now.